Good afternoon, everyone. My name is Joey. I am a developer from Alibaba, and today I'm going to talk about VA garbage collection logs. So a little bit of background. Why are we looking into these logs? Well, for starters, Alibaba is using Node.js. It's probably the company with the most Node.js developers in China. We use Node.js mostly to build application servers on top of our infrastructures. At the moment, Node.js is running on thousands of machines in our clusters, and you can find it in almost every business unit of Alibaba. But in our company, Java is still the mainstream, even for the application servers. We chose Node.js for productivity, but we can't be confident about this choice unless we can be sure about the availability of our Node.js applications. Even though most of the times the bottleneck lies in the database layer instead of the application layer, since most products from Alibaba serve a huge traffic, every optimization counts. So one thing different about optimizing JavaScript in the server than in the browser is how much more crucial garbage collection can be. Because server-side applications tend to run longer and handle more data than average client-side applications. Garbage collections can eat up the CPU, making your application less responsive, or they can hold on to your memory, affecting other processes on the same machine. When misled by developers, they can lead to memory leaks and even crash your processes. That is why most Java developers in Alibaba know at least a few things or two about JVM and its garbage collection. But our Node.js developers usually come from a front-end background, where garbage collection is less of a big deal there, so we still need to catch up on that. And that is why we started to look into the garbage collection of V8. If you are interested in the story of Node.js at Alibaba, you can check out this interview. So, what tools do we have if we want to take on performance problems caused by VA garbage collections? Well, most tools we use come from the Chromium, but they are more about optimizing front-end applications at the moment. We have Heap snapshots, Heap timelines, and allocation timelines, but they are more about allocations, less about garbage collections. And you could get lost in all the details they capture. We have CPU profiles to know when the garbage collections are triggered, but it doesn't tell you how much. It doesn't tell you what these garbage collections do. And this could have a significant impact on the performance, so it might be hard to get them running in staging or production environment, even if you can only reproduce your problems there. But luckily, VA provides garbage collection logs for us. It's not documented. You have to use command line flags to get them, but they can give you more knowledge about Heap than a number of memory usage without all the details of Heap profiles. They can help you verify your fixes by displaying the patterns of garbage collections in your applications. It's no silver bullet, but it's definitely a nice to have in your box of tricks. So this talk is based on the versions of VA used by Node v4 and v6 LTS. There are a few subtle differences in older versions of V8, but most of these talks should still apply. So to make sure we are on the same page, what is garbage collection exactly? Well, it's the process of cleaning up useless objects and freeing up memory for allocations. In V8, most objects live on the heap, and when an object can not be reached by traversing pointers from the root objects, it becomes garbage and needs to be collected in later garbage collection cycles. So when you are writing C++ code compiled by GCC, you need to look into the code and decide when to free the memory before it's even compiled. But when you are writing JavaScript code run by V8, It's the garbage collector that needs to look into the heap and decide when to free the memory at runtime. In V8, most garbage collections are triggered by allocations. When V8 can't allocate an object because we don't have enough memory for it, it will collect the garbage, hopefully freeing up some memory, and try again. If V8 still fail after 2 collections, it will go into panic mode and do a more thorough garbage collection, invoking weak callbacks, trying to squeeze out all the memory it can. If it still don't have enough memory after this, then VA would just give up and crash the process, saying we run out of memory. So how can garbage collections have an impact on the performance? That's because when doing garbage collections, the JavaScript engine might need to pause the program execution so it can look into the heap or move memory around. This pause can come into different flavors. For stop-the-world garbage collections, the whole program is gonna be freeze throughout the garbage collection cycle. But if we can somehow divide the task into small pieces, we can make the garbage collection incremental. We can have the program run a little while, then do a little bit of garbage collection in a much smaller pause, and then resume the execution, and so forth. So in this way, the program will be a lot more responsive. And if we can take a step further and organize the heap in such a way that we can run the program on main thread while doing garbage collection on another thread, then we will have a concurrent garbage collector. We can even make it parallel by using multiple garbage collector threads. In VA, there is more than one garbage collector, so we have all these different kinds of pauses during different stages of the garbage collections. People who build garbage collectors have noticed that most objects die young, and those who don't tend to live forever. This is called the weak generational hypothesis. Based on this observation, we can check those young objects more frequently in order to reclaim memory in time, and check the old objects less frequently so we can save the CPU. There are a lot of language implementations following this strategy, and VA is one of them. The garbage collector responsible of cleaning the young generation will stop the world, but the one cleaning the old generation has a mixture of incremental, concurrent, and parallel garbage collection. So the memory managed by VA looks like this. On the heap, we have 2 generations of objects and 5 spaces. The young generation only has 1 space, the new space, which consists of contiguous memory pages. Most objects start and end their lives in this space. The new space is divided in half. Each one is called a semi-space. The old generation have 4 spaces dedicated to different kinds of objects. The old space contains objects that survives more than 2 garbage collections in the new space. And if V8 thinks that some objects are going to be promoted anyway, then they will be allocated in the old space. The code space contains executable code compiled by V8. The map space contains the maps, also known as hidden classes, which contain metadata about object layouts. The large object space contains objects too large to fit into a page or in any other spaces. VA has a memory allocator to manage the pages it receives from the operating system. And for Node.js, we have some external memory managed by the C++ code, like the buffers. So when allocating this memory, we will report to VA about the amount of memory allocated and register callbacks to clean them up when the corresponding JavaScript objects become unreachable in the VA heap. Okay. So VA puts a limit on the memory it can use. By default, the two semi-spaces in the new space can each have at most 16 megabytes of memory, and the whole old generation can have no more than 1.4 gigabytes of memory. Since we can move objects from the new generation to the old generation, we usually run out of memory when we hit the limit of the old generation. If you need more memory than that, you can configure these limits via command line arguments. VA uses the scavenge garbage collection to clean up the new generation. As we mentioned before, the new space is divided into two equally sized semi-spaces. Only one of them is active at a time. When VA needs to allocate a new object and the active semi-space is full, it will start to scan references from the root objects and copy the reachable objects to the other semi-space. If an object has already survived a garbage collection before, then it will be moved into the old space. After the garbage collection, done working all the pointers to the new space it can find, the previous active semi-space will be left with dead objects, and the other semi-space will be turned active. The old generation is managed by a different garbage collector, so when a certain memory threshold is hit, VA will start to identify the live objects on the heap and leave marks on them. When the marking is done, VA will start to reclaim memory either by sweeping or compacting. When sweeping a page, VA will add memory blocks taken up by dead objects into the free list, so the next time it needs memory from this page, it will pick a block from the free list, overwriting the dead object with another object. A page could be heavily fragmented after a few sweepings. Then VA can instead move all the live objects in this page into a new page or another less fragmented page. This is called compacting, and after compacting, the page left behind can be returned to the operating system. So in summary, GC poses in VA looks like this. Most of the times we allocate new objects in the new space, and when it's full, VA will start scavenge garbage collection. This should last only a few milliseconds because the new space is supposed to be very small. VA can grow the size of the new space as the program keeps allocating more memory. When a memory threshold is hit, VA will start to mark the liveliness of objects. This process is incremental, and again, each step of marking should last just a few milliseconds. If the liveliness of an object is changed after it's been marked, something called the write barrier will be triggered to remind VA of checking it later. So when the marking is complete, VA might not jump into sweeping immediately. It will wait for the right time to start sweeping. Since we are sweeping dead objects, this should not interfere with the program execution and should be safe to parallelize. So sweeping is both concurrent and parallel. After sweeping, VA will do a scavenge garbage collection in the new space, since we have also marked the young generation in the marking phase. And this will need to pause the program for a few milliseconds. VA will also, sorry. So VA will also compact the fragmented pages. VA will also compact the fragmented pages, and this should last just a few milliseconds too. Okay, so we have talked about the basics of VA of VA's garbage collection. Now, how can we get the logs of this and use them to analyze our applications? Well, the logs can be turned on with command line options. There are more than one option, each with a different output. We are only going to talk about the ones that we found to be the most useful. So there is trace GC, which will print a line for each garbage collection, describing the when, the how, the and what, and why of this garbage collection. And there is a verbose version of it, which gives a summary about each space in the heap after each garbage collection. There is also Chase GC MVP, which prints dozens of name value pairs for each step of GC, like how much time we spend on sweeping, how much memory has been promoted, something like that. If you want to know more about it, you can always dig into the source code. Okay. So next, I am going to talk about how to read these logs. The output of trace GC looks something like this. We'll have one line of this for each garbage collection. On each line, first we have where this garbage collection is coming from. There is a process ID and an isolate ID. An isolate is like an instance of V8. Each has its own garbage collector. The green one there is when this garbage collection takes place. That is how many milliseconds has passed since the process has started. Next, we have what type of garbage collection this is. As we mentioned before, we have two types of garbage collection at the moment, scavenge and mark sweep. The purple one is how much memory has been reclaimed during this garbage collection. On the left of the arrow, we have the memory usage after the garbage collection. The numbers outside the parentheses are the total sizes of all objects. The number inside the parentheses are the number that VA actually allocated from the operating system. The number on the right-hand side of the arrow is memory usage after this garbage collection. So the numbers inside and outside the parentheses are different because, as we talked about before, the spaces are paged and can be fragmented. After that, we can see how long this garbage collection takes. So before the slash, we have the time the program has been paused. On the right of the slash, we have the time we've spent on external memory. And following that, we have the reason of this garbage collection. As we talked about before, most of the times is allocation failure. And the next one is the verbose flag. This has to be used with trace GC together to get the output. So for each garbage collection, this would print several lines. The memory allocator, as mentioned before, is an abstraction that VA uses to manage memory allocated from the OS. The use memory is the memory VA has already allocated from the operating system. And the available memory is how much more memory that VA can get from the OS. Then we have the statistics about each space for most of them. Used memory is how much memory the objects has occupied in this space. Available memory is how much memory left in the pages. And committed memory is the sum of these two. Notice for the new space, since we have two semi-spaces, the committed memory is the twice of the sum. The available memory of the large object space is much bigger because that's the available memory from the memory allocator minus the memory can use to put objects like the page headers. Then we have the total of these spaces, like amount of external memory reported by the user code, the time we've spent on each garbage collection. Some log would report a heap growing factor that VA uses to calculate threshold for next marking. Okay, the last one is trace VGC MVP and is kind of self-descriptive. So I'll just leave it there since we don't have enough time for it. Notice this use shorthands for the names of garbage collectors. MS means mark sweep and S means scavenge. So here are some performance problems we have found that are related to garbage collections. We've seen tons of garbage collections eating up the CPU. This could be cache misses caused by inappropriate caching strategies, or it could be excessive deep clones. Some applications do that to avoid mutations. Some of our applications handle huge chunk of RPC payload, and the serialization and deserialization could generate a lot of large objects, blocking up the large object space. And there are some peculiar cases like a bug in our templating engine keeps compiling unnecessary JavaScript functions from the templates, and these functions live in the code space. So we can see the code space keep growing in the garbage collection logs. Some of our external clients use callbacks and closures to build applications, and this can be problematic in long connections because VA doesn't minimize the closures at the moment. So these closures can keep a lot of irrelevant objects referenced. Then VA will keep promoting these objects to the old space. And when you hit the limit of your old space, this can crash your process. And there are some tools to help you read the garbage collection log. We've open sourced our parser. It's up on the NPM, and it's ready to use for people who already have applications running in production. We also have a visualization for it, and we plan to open source that too, but it still needs a little bit of cleanup. I've written some blogs on this topic before. They are a little bit deeper than this talk, and I'm going to translate this into English as part of our documentation. There are some new flags available in newer versions of V8, but we probably have to wait until the next LTS to use them in production. I'm running out of time here, so I'm not going to talk about it in details. Thanks for listening. You can find me on Twitter